Hello. So now before we start our discussion of stoichiometry, we're going to look at the mole. Okay. When I talk about the mole, I'm not talking about little furry creatures like this or this picture shown up here. I'm talking about a chemical quantity that's used in chemistry. And so when we look at a chemical equation, as mentioned before, the coefficient represents the number amount of that. So this is saying I have 2 aluminum atoms reacting with 3 chlorine molecules, give me 2 molecules of aluminum chloride. Now if you was actually going to go into the lab and you wanted to make aluminum chloride and you wanted to not have any excess reactant, you wanted to react them together on a one-to-one basis where you didn't have anything left over, you can't exactly measure out 2 aluminum atoms or 3 chlorine molecules because atoms and molecules are so small. So we need a unit or some way we can actually measure this stuff out so we can actually do it in the lab. And so that's where the mole comes into play. And so the mole is a number just like a dozen is a number. So we know a dozen represents 12. Well, a mole is 6.02 times 10 to the 23rd. And that number is known as Avogadro's number, and it's the number of carbon atoms, exactly 12 grams of carbon-12, so that's how they came up with that number. And this number is so large, if you think about scientific notation, you're taking this decimal point here and moving it 23 places to the right, so you have a lot of zeros there. So a very large number. It's even larger than if you take all the grains of sand and all the world's beaches and all the world's oceans. Avogadro's number is still larger than that total. So, very large number. And we can use that when we look at the chemical equation. So we go back and look at this chemical equation. This can also say, it can still represent 2 atoms of aluminum combined with 3 molecules of chlorine, but it can also represent the moles now, but it's been on a larger scale. So 2 moles of aluminum reacts with 3 moles of chlorine to give 2 moles of aluminum chloride. So, and Avogadro's number is, if you have 1 mole of something, anything, you have Avogadro's number of that substance, just like if you had a dozen or anything, you'd have a dozen of that substance. So we can use this as a conversion factor. So here, before we get to looking at atoms and molecules, let's look at bicycles. So suppose you have 2 moles of bicycles, how many bicycles do you have? Well, let's just say if it said, suppose you have 2 dozen bicycles, how many bicycles would you have? Well, you know a dozen's 12, so 2 times 12 would be 24, you have 24 bicycles. Same thing with Avogadro's number. I'm going to do this with dimensional analysis though. So, write down my measurement, 2 moles of bicycles. Now I know 1 mole of anything, I have Avogadro's number, so I can say 1 mole of bicycles, I have 6.02 times 10 to the 23rd bicycles. So I just take 2 times Avogadro's number, so I get 1.2 times 10 to the 24th bicycles. Now if we just apply this to a compound now, suppose you have 2 moles of iron, how many iron atoms do you have? Well, change bicycles to iron, 2 moles of iron, 1 mole of iron would be 6.02 times 10 to the 23rd iron atoms. Now there may be some confusion here when you do this. Okay, does moles represent atoms or molecules? Well, it depends on what you're asking for here. Does this exist as atoms or molecules? If it said 1 mole of water, then it'd be Avogadro's number of molecules. If it says iron, so iron's an atom, so that's why it's atoms here. So you can see Avogadro's number, specifying number of atoms or molecules, depending on what this substance down here is. So then that would just become the same atoms. Well, let's look at this one. Suppose you have 2 moles of bicycles. How many, should just say bicycle tires do you have? We don't have our bicycle, well, I guess you could. But, so how many bicycle tires do you have? So I'm going to say 2 moles of bicycles. So if you're doing dimensional analysis here, what you have on top here needs to cancel out with what you have on bottom here. So if you have moles of bicycles, I need moles of bicycles here. So now it's asking how many, so I'm going to use Avogadro's number. And whatever this mole is of, that's Avogadro's number of that substance. So if I have 1 mole of bicycles, it's 6.02 times 10 to the 23rd bicycles. But my question does not ask how many bicycles, it asks how many tires. So I'll take it a step further now and say, okay, 1 bicycle, how many tires do I have? Well, a bicycle has 2 tires. So now it cancels out and I'll be left to how many tires I have. So it's the same thing if you have a molecule. If you have, if it asks, I have 2 moles of water, how many hydrogen atoms does it have? Well, I put 2 moles of water here. 1 mole of water is 6.02 times 23rd molecules of water because H2O is a molecule. Then in 1 molecule of H2O, it's H2O, that means I have 2 hydrogen atoms. So in 1 molecule of H2O, I have 2 H atoms. And I get how many hydrogen atoms I have. So 2.4 times 10 to the 24th tires. So let's go ahead and apply it to some chemistry. So consider propane, C3H8, used for gas grills and torches. If you have 3.5 moles of propane, how many propane molecules do you have? So I have C3H8, so that's a molecule. So 1 mole of C3H8, I have 6.02 times 10 to the 23rd molecules of C3H8. So I just take 3.5 times Avogadro's number, just like it said, if I had 3.5 dozen of propane molecules, I take 3.5 times 12. 3.5 times 6.02 to the 23rd. So 2.1 to the 24th. And that's molecules. B says if you have 4 moles of propane, how many hydrogen atoms do you have? Again, I'm given 4 moles of C3H8. How many hydrogen atoms? Well, I have a mole of C3H8, so that's a molecule. So Avogadro's number molecules okay. So my moles of C3H8 cancel out. My molecules will cancel each other out. It says how many hydrogen atoms, so I have to look at my formula here. C3H8. So in 1 molecule, I have 8 hydrogen atoms. Okay. So I'll take 4 times Avogadro's number times 8. So I get 1.9 times 10 to the 25th hydrogen atoms. Now if we look at molar mass, so recall that each element in the periodic table has atomic weight underneath it. This atomic weight in atomic mass units. The molecular weight or molar mass of a compound is the sum of the atomic weights of its component atoms or ions. So like if you looked at C6H12O6, you look up carbon in the periodic table and it's 12.01. So you take 6 times 12.011. Okay. You have 12 hydrogen atoms. So look up 12 in the periodic table times it by the atomic weight. Oxygen, if I look it up, is 15.9994. So multiply by 6, I have 6 of them. Then I'd add all those together and I get what's known as a molar mass or the molecular weight of my compound. Now, we can use this as to help us when I mentioned, if you go into the lab and you want to do a chemical reaction, what can you measure out? This allows you to convert to something that you could weigh out on a balance, because this molar mass, this atomic mass in the periodic table, tells you the number of grams in 1 mole of a substance. Okay. And so our units are going to be grams per mole. And so, if we look at here, like sodium chloride is 58.5 grams per mole, water, oxygen's around 16, hydrogen's around 1. So 2 hydrogens would be 2 plus 16 is 18. And so this molar mass can be used as a conversion factor to go from moles to grams and vice versa. So you can measure something out on a balance. And so our balanced equation is in moles. What we can do in the lab is in grams. And so those two things are going to be able to work together. And so to be able to do reactions and to see how much product we made or how much reagents we made to start with. So that's all what stoichiometry is about. So let's go ahead and look at some problems to convert grams into moles, because we'll be doing a lot of this in stoichiometry. It says, suppose you have 2 moles of iron. How much will 2 moles of iron weigh in grams? So I have 2 moles of iron, so I'm going to look up iron in the periodic table. So if I look up iron here, 55.845. So, and it's grams per mole, and so I want the moles to cancel out, so that means I want the grams on top. If this was grams, then my molar mass would be down here because I would want the grams to cancel out. So 2 so 111.69. We mention how many significant figures I want to go to. Say 112. I'm just going to say 110. I'm just going to go to 2 significant figures. Say 110 grams of iron. So consider again propane, C3H8. How much does 2.6 moles of propane weigh in grams? Okay, I need the molar mass of propane. I'll look up the atomic mass of carbon in the periodic table. See, it's 12.011. Look up hydrogen. 7, I'm just going to round it off to 8. So I'm going to add those together. It's around 44.1 grams per mole. So I want the moles to cancel out. So I put the moles on bottom. So I take my atomic mass, multiply that by 2.6, get around 115, 114.6. Around it to two significant figures. Also get 110 grams. So I get 114.6, so I did round down to so I could just have two significant figures. Now this says how many molecules of water are there in 10 grams of water. It's getting a little more difficult here. So 10 grams of water. So how many molecules? Well, I can use the molar mass to see how many moles I have. This is grams, I need grams on bottom here. Grams per mole. It doesn't say how many moles. It said how many moles of water. 10 divided by 18 would be my answer. It says how many molecules of water. Well, I know in 1 mole of anything, and Avogadro's number. Well, water is a molecule. So in 1 mole of water, there's 6.02 times 10 to the 23rd molecules. Moles cancel out. I'll be left with my answer. I'm going to go to 3 significant figures. So I get 3.34 times 10 to the 23rd molecules. It says how many aluminum atoms are there in 10 grams of aluminum oxide? Getting even more difficult now because I'm not given the formulas. So I have to go way back and remember how to draw formulas from names. So aluminum oxide. I know oxygen from the group number it's in the periodic table has a 2 minus charge. Aluminum to group 3, so it's a 3 plus charge. So to get the charges to balance out, my formula must be Al2O3. So I have 10 grams of Al2O3. Now again, I want to look at the periodic table. Now, looking at aluminum, 26.98. I'm going to take 3 times 16. .96 grams per mole, or you call it 102. So that's grams per mole. That says how many aluminum atoms. this, what I have moles of, is not an atom, it's a molecule. So I have to use that as my conversion. So 1 mole of Al2O3 is 6.02 times 10 to the 23rd molecules. Okay. Now the question asks for aluminum atoms. So I say 1 molecule of Al2O3. It's Al2O3, so there's 2 aluminum atoms in that molecule. And you just cross the molecules. Okay. So now I'd be left my answer in the aluminum atoms. So I take 10 times 6.02 to the 23rd times 2 divided by 101.96. And I should ask 3 significant figures, 1.18 times 10 to the 23rd aluminum atoms. So that's it for some problems where using the molar mass to go from grams to moles or from grams to molecules even. And so that prepares us to go ahead and jump right into stoichiometry, which I'll cover in the next lecture.